Bismillahirrahmanirrahim. Assalamualaikum and hi. So today I'm going to present about our group project for subject digital electronic from section 2, and our project title is 3-bit synchronous counter using JK flip-flop. And our members include of me. My name is Jasmine Jaafar, and Yuan, and also Natalie. And for our introduction, a flip-flop is a type of sequential devices that are function as storing one binary bit. By interconnecting a variety of flip-flops, a more general sequential device can be constructed so that able to process one or more binary bits, which normally known as counters and register. A synchronous counter was defined as the counter whose output bit changes its state simultaneously with no ripple. In this term form of clock pulse, thus all the flip-flops change state simultaneously in parallel arrangement. It advances to following output state on the PGT, positive current transition, of the input clock. The output of the counter could also be preset to a high or low level. The low level of output for the counter reach at the parallel and could enable the input of counter disable the counting action. And for the literature review, the design and operation of synchronous counter up has been well researched. Bauer certainly as mechanism and internal design of synchronous counters for displaying decimal values on 7 segment displays. He used a total of 7 JK flip-flops to design modular 65 synchronous counter. By showing decimal value on the segment display by cascading two counters together with the last digit, ones digit, counter provides the clock pulse to the second digit, 10-digit counter. Bauer also introduced the partial decoding mechanism to clear the decimal in each counter after the number 65 in decimal. He applied an external synchronous clock to the ones digit counter to count from 0 to 9. Then he located a logic AND gate at the 6th state of both counter to clear both counter. And this is called as cascaded connection of counter because both counters needed to be cleared when the count reached 65. So this proposed that this mechanism is sufficiently practical top 3 design and types counter to show the output of counter in decimal form. So that is all from me. We continue with my other crew member.
My name is Natalie, so now I'm going to present on the simulation demo. The software that we are using to design our circuit is the Proteus Professional. So it is a software which can be used to draw the schematic PCB layout, code and even to simulate the schematic. Okay, so now I would like to show the simulation demo on our 3-bit synchronized up counter circuit using JK flip-flop. So as we can see from here, this is our complete design circuit. Okay, now I would like to run the circuit. And then we can see that the binary is changing and the LED display also displaying the number counting up. And when we check on our digital oscilloscope, we can see that when the number and binary is changing, the clock pulse is also changing. Alright, so that's all for our simulation demo. We will show the detailed designing procedure in another video. Okay, so now we are going to the result and discussion. Okay, so from the simulation demo we present just now, as a result we will get the 3-bit synchronized counter up. So from here we can see that there's a binary number with their respective decimal number. Okay, so now I would like to introduce the state diagram. So from the state diagram we can see that after the number 7, which is a 111, it will go back to 1 and then it will continue the consequence number. So this looping, it will continue until the stop button is pressed in the simulation demo. And then also we can easily construct this 3-bit synchronized up counter by just using a logic AND gate. Okay, so for our discussion part, we will split into 2 perspectives. So the first perspective is the demonstration on step designing circuit layout. And then the second perspective with the analysis of output binary and clock pulse timing diagram. Okay, so now we are going to look at the first perspective, which is the demonstration on step designing circuit layout. Okay, so the first step is we're going to draw the state diagram, which I already shown earlier, and then the next step is construct the next step and transition table. Okay, so for the third step, we will construct the K-map. So first, we will construct the K-map for J0 and K0. So J0 and K0 is the input of the first JK flip-flop. After that, we will get J0 equals to 1, K0 equals to 1. So which means that the both input terminal of the first JK flip-flop is connected to the clock at the clock state of 1. Okay, so next we will construct for J1 and K1, which is the input for the second JK flip-flop, and then we will get the result of J1 equals to Q0 and K1 equals to Q0. So from here we can see that the both input terminal of the second JK flip-flop is connected to the output of the first JK flip-flop. Okay, so for the last one, which is J2 and K2, it is the input for the third JK flip-flop. And then from the K-map, we can see that J2 equals to Q1 times Q0 and same as K2. So we can use the logic AND gate to represent the symbol multiply. And so that it means that the output of the first and second JK flip-flop is connected to the input of the logic AND gate, and then the output of the logic AND gate will be connected to the input of the third JK flip-flop. Okay, after that, looking at the first perspective, now we are going to look at the second perspective, which is the analysis of output binary and clock pulse timing diagram. So at the left hand side, we can see this is the digital clock pulse timing diagram from the oscilloscope, and then we will redraw the clock pulse timing diagram to have a more clear vision of the clock pulse. So the yellow field represents the clock pulse, the blue field represents the output of the first JK flip-flop, the pink field represents the output of the second JK flip-flop, and then the green field represents the output for the third JK flip-flop. Okay, so now here I'm going to explain how we analyze the clock pulse timing diagram. Okay, so the first thing we will do is we insert all the J and K, which is the input for each JK flip-flop from the transition table. And then in the transition table here, we can see there's a X symbol here. So the X symbol is known as a don't care condition, which can be either 0 or 1. But when we look at our K-map, we can see that actually J and K, they both have the same condition for the 3 JK flip-flop. So which means that we can change the X to their respective partner state. For example, when J1 is 0, K1 is X, we will take K1 as 0 also, because J1 and K1 must be in the same. How we analyze the clock pulse timing diagram? For example, we will take J1, K1 for clock 0. Okay, so at clock 0, J1 is 0, K1 is 0. And then we refer to the truth table of the JK flip-flop. It shows here when J is 0, K is 0, the output will have no change. So which means in the next state, it will hold the same state as the previous state. And then for clock pulse 1, when J1 is 1, K1 is 1, when we refer to the truth table, it shows that the output is toggles. So what is meant by toggles? Which means that at the next state, it will change their state, which is not same as the previous. If previous is 0, then the next it will toggle to 1. Okay, so that's how we analyze the clock pulse timing, and that's all from the result and discussion part. Thank you.
Hi, I'm Myron, and I'd like to present the part of the conclusion. As a conclusion, we are using all the knowledge that we have learned to complete this project. Thus, this project also can be used in further, such as like digital clock or pulse generator, parking counter in a big parking area, automotive RPM counter, and so forth. Last but not the least, we also know that all the gates were triggered by one common clock pulse. So in short, counter itself is the widest applications of the flip-flop. And that's all my presentation. Thank you.